I'm Jaravi.
I'm Jacob Kidd.
Brandon Mabry.
Cody Webster.
And I'm Jaleel Thompson.
And we'll present you guys the TTI tool locator system.
The motivation for this project, we were given the idea of DIYers and tradesmen often have very disorganized workspaces, garages, and work vehicles. And so we wanted to develop a system that is able to give the customers a way to find their products easily. We were tasked by the company TTI to try and solve this problem in about a 3-month period, using the knowledge that we had previously learned in our classes here at Clemson.
Some of the goals and deliverables for this project, we had to create a system of tags and one finder. The students had to construct a single finder able to find at least 2 tags, and it must be able to differentiate between the tags and only locate one tag at a time. The tags must be passive and not active, which means they do not require the use of external power in the form of batteries. And the finder shall give an auditory or visual indication when a tag has been found.
Hardware designs requirements that the tags need to be 1 inch by 1 inch. We exceeded that. We have the smallest tag that we have is 2 centimeters by 3 centimeters, which is a small metal passive tag. Finder must be able to detect any tag within 20 feet. So with even 3/4 of the power, read power, we can read up to 15 to 16 feet with the patch antenna, but with an antenna array, full power, and the patch antenna at full power, we can read 25 to 35 feet. And we tested that in the hallway. Finder must only detect tags within 50 or 45 degrees of pointed direction, so the beam width of the antenna need to be within 45 degrees. The higher that you go in dB on antennas, the tighter the beam width would be. So we chose 6 to 7 dBi. If the finder is a custom device, the device must be battery powered and have a sleep current no greater than 100 microamps. We exceeded this as well, created a small circuit consisting of a PMOS and an NMOS to actually get an absolute 0 current whenever the system is idling for a set X amount of time, it will automatically turn off and it's 0 amps. Use a maximum of 3 buttons to run the device, and the LCD screen needs to be a certain size. So we have 3 buttons, enter.
This is the final design that we went with. We decided to go with a design that closely resembled a handheld power drill or a radar gun. We felt that this was very intuitive for the user, kind of a point and shoot idea. So the total device is comprised of 6 different parts. This is simply for sake of assembling and all the wiring. So all the electronic components are comprised in the head, which is up there at the top. That's where all the circuitry is for the LCD screen, the buttons, and everything. And then towards the bottom is the power bank, which is where we have an external battery which is powering the system. But this is how it is all assembled.
We called Arduino 1 Arduino P, and Arduino number 2 was Arduino Q. And here are the associated flow charts for each of those Arduinos.
So the electrical design, we have a picture of an overview of the internal workings of the RFID reader that we've done. The power saving circuit, like I mentioned before, consists of a PMOS, a power PMOS, which has a rating of 30 amps, and a signal NMOS to cut off the circuit. and that's what regulates basically the power saving mode when it comes to our system. The buttons on the carrier are connected to the breadboard, are connected to the Arduinos as well. So they're in line or in series with the circuit that we've done. So everything only turns on, even the fans, the RFID reader, the LCD all turn on when the button is pressed. After 2 seconds, you have to wait 2 seconds for the system to latch on, then X amount of time, it'll turn off. Buzzer is connected to the breadboard in Arduino P. It's just some little fun thing that we added to when you turn on the device itself. It gives an audible reading to the user that, hey, I'm turning on. Wires from Arduino P and our reader and antenna that we're using a Arduino Uno for the LCD connected via serial command with the Arduino Mega, that's basically running the RFID shield. The pin 36 and the transceive and receive pins are connected to the P, like I said, via serial command. Antenna is attached in the front enclosure. That's the best optimal way that we can have the antenna positioned for a patch antenna, which is a circular polarization. It's better than linear when you have fluctuations of tag orientation on specific items. Far field antenna is being used. Like I said, far field is more of backscattering, whereas near field is more induction induction and magnetics.
So this is a demo of our design. Brandon's gonna go ahead and turn it on.
Turn it on, you hold it down this red button for 3 seconds.
So it pops on there. He's gonna press enter to begin. He's gonna select the down button to see which tool you wanna find. So right now we're gonna search for tool A.
Oh, sorry.
So now it's searching for tool A. You see it says tool A not found. And we're gonna show tag A in the read distance. You can see it switched to found tool A. You're gonna go back to the menu. You're gonna press down. You're gonna select tool B. I'm gonna select tool B. Yeah, press it again.
Oh, my bad.
Hold it down too long. So you see the device is searching for tool B and has found tool B in the read distance. So you go back to the menu and select tool C. So the device is now searching for tool C, and you can see it's automatically found it in the read distance.
Go ahead and move out of the way so they can see that it...
So you can see when Jacob steps out of the distance and the angle that the reader is searching, it says tool C not found. And that is a demo of our final project. The challenges and bottlenecks that we faced during this project were time constraints. We were not able to manage all of our minor issues that we would have liked to address in the final design and presentation, and we wanted to implement the add a new tool program, but we ran out of time to implement this into our design. Another challenge that we faced during this project was the battery size and getting enough power to efficiently and effectively supply all of our components with enough power to get the most out of our design. And then the final challenge that we faced was the distance and range that we were able to get out of our antenna arrays and RFID readers given the battery that we had.
Now I'd like to go more in depth. So if you guys want to build onto this system, our initial system, the The best way to do that is, so for battery wise, the RFID reader pulls 1 amp. The Arduinos together pull about 300 milliamps. So we need something that is sufficient enough for around 2 amps and 5 volts output. A steady power, otherwise the reader will brown out the supply and it'll fluctuate on and off, and that's not good for the entirety of the chip. For effective range, we found out through research and trial and error that the antenna array actually versus the circular patch antenna gives us a larger reading when it comes to tag searching. We've reached up to about 35, 36 feet at full power versus 20 to 22 feet with the circular patch antenna at full power. Other than that, that's all. Well, that and heat sinking. If you guys figure out just a better way to distribute the heat versus the way that we have it on chip mount, maybe a board mount would work better, and probably bigger fans, obviously. This will cool down the system, as in cooler temps will allow the system to read at full strength for a longer time.